we got notes over exponential functions. This will start our unit with exponential functions. We've seen them a little bit before. We're going to go through and get the basics and go over these Monday. So hopefully you're watching this video right now, which you are if you're watching it. So yeah, okay. We're going to go and let's talk about exponential functions. So what an exponential function is, the parent function, oops, let me grab my pen here. The parent function we'll see down here is y equals b raised to an x power. So an exponential function, the x is in the exponent. So let's look at just a few examples here. If we were going to try to find the slope of this, we would do our little wings. We would do our wings over here, and this goes up 1, and this goes up 2, and this goes up 4, this goes up 8, this goes up 16. Okay, as you see, it's not the same. Over here, it's 1, 1. 2 to 3 is 1. Okay, those are staying the same. These are not. If you remember our lines, the slope would be the same. This and this would be constant throughout, but with an exponential function, you can obviously see here that it's getting bigger and bigger and bigger. Okay? And that's what it said. That's basically what these first blanks are talking about. Exponential functions, they involve repetitive multiplication because you keep multiplying. In this case, we're multiplying by 2 every time, rather than addition like in linear. Because when we have a linear, we add. We would be adding 2. So this would be like 1 to 3 to 5 to 6. But it's not. It's being multiplied. That is an exponential function. And what we looked at right here, that's the delta y, that's the change in y. So how much did the y change? It changed by 1, it changed by 2, it changed by 4, it changed by 8, it changed by 16. That's the change in y. The ratio of y, which is something we're going to make sure we're looking at, the ratio is, for instance, 2 over 1. So that would be 2 over 1. If I go from here, 2 over 1. If I go from here, that'd be 4 over 2. 4 over 2. If I go from here to here, that would be 8 over 4. And if you notice, the ratio, 2 over 1, that equals 2. 4 over 2, that equals 2. 8 over 4, that equals 2. The ratio stays the same. Okay, and that's a big thing to notice in exponential function. The ratio has got to stay the same. It's got to be the same. So right here, here's just a few basic examples of exponential functions. And the first one is y equals 2 to the x. So you could plug this into your calculator. You could do it. You could plug values in for x, and you would find that the graph would be coming out here. Then it would cross at 1, and then all of a sudden it'd start going up, and that's why it's called an exponential function. It grows dramatically because, again, being multiplied again and again and again. All right. Y equals negative 3. 3 to the negative x. Now the exponent is negative. When the exponent was positive, so it was a positive x, it was growing. When the exponent is negative, you'll actually see that this graph, instead of growing, it gets smaller. Still the same curve. It's still, if you look at it going from right to left, it's growing, but you always look at these graphs going left to right. So I'm looking at this graph left to right, and it's getting bigger. I'm looking at this graph left to right. Okay, it's big, and all of a sudden now it's getting smaller and smaller and smaller. Okay, the same thing here with a fraction. If your base is a fraction, it's going to also get smaller and smaller and smaller. And you can always plug these into your calculator and look at them and see those graphs as well. You can plug x values in and get some points and see what it looks like. Whenever this gets bigger, that's what we call growth. And we'll have more notes on these Monday. Growth, whenever it gets smaller, that's what we call decay. It's getting smaller. It's decaying. So those both would be decay. Okay, and that's what this says right here. When it's positive, the exponential is growth. When the exponent is negative, exponential is decay. And then when the base is between 0 and 1, that means it's a fraction. Okay, it's a fraction. Then the exponential is also decay. Now, looking down here at the bottom, got it in capital letters, exponential function. Here is your parent, there's your parent function. Y equals b raised to x power, where b is the common ratio. So a ratio, just like we looked at earlier up here, it was 2. A ratio is 2. So b is your ratio, and the variable is the exponent. So the x will be in the exponent. All right. Looking right here, let's see. Okay, we're going up. This is 1. Going up. This is 1. Going up. This is 1. Okay, yeah, those are just going up by 1. How much is this going up by? Well, this went up by 3. And then from here, it went up by 3. And then from here, it went up by 3. If you look at this, the change in y stayed the same. Just went up by 3, went up by 3, went up by 3. If you look at the ratio, okay, the ratio would be 13 over 10. And then it would be 16 over 13. And then it would be 19 over 16. And if I plug this into my calculator, I'll see that, this would equal 1.3. This would equal 1.23 and a lot of decimals. And really, that's all you need to see right there. I think that's like 1.1 and so forth. The ratios are not the same. So like I have right here at the bottom, this is not the same. So this is not an exponential function. The second example here, we're not going to use these numbers that were given to us. We're going to use instead 9, 12, and 16. So make sure you make that correction. So again, it's going up by 1s over here. Over here, you went up 3, and then you went up by 4, so it's getting bigger. But let's look at the ratio. Let's look at the ratio: 12 over 9 and 16 over 12. If I plug those into the calculator, if I do the division, I'll see that they're both 1.3 and some change, and 1.3 and some change. 1.3s, okay, that's great. They're exactly the same. So if they're the same, then yes, this is an exponential function. So again, we're looking at the ratio. And how do I get the ratio? I just put 12 over 9, 16 over 12. Those ratios are the same. This is an exponential function. All right, looking at the back side here. This wants us to complete the table and graph it. So a couple different ways you can do this. Easiest way is to take, and again, we're not going to use the one that was given here. We're going to use this example right here. Y equals 3 raised to the x power. Take this, plug it into your calculator. The easiest way. Take it and plug it into your calculator. 3 raised to the x power. If I didn't have a calculator, so right now at home you don't have a calculator, all you have to do is, okay, 3, what is x? 0. Anything to the 0 power, that would be 1. 3 raised to the second power, or excuse me, the first power. That was 0. This is raised to the first power. 3 raised to the first power, that would be 3. 3 raised to the second power, well, that's 3 squared. 3 squared is 9. Okay, and you can see a pattern here. 1, and then it went up 3, and then it went up 6. So I'm betting it's about to go up 9. And then 3 cubed is 3 times 3 times 3. See that is 27. And going up 3 to the 4th power. So right now we're thinking 3 to the 4th power. 3 times 3 times 3 times 3, that would be 81. And if I did it to the 5th power, that would be 243. Okay, so I just got some points and values. That's how you do it by hand. Again, you can plug in the calculator, look at your table. That's probably the easiest way. Now, if I wanted to graph this, 0, 1, okay, that's that point right there. 1, 3, that would be that point right there. 2, 9, will be way up here. And then it just gets really, so it's getting really big up there. And it come down right there. And if you graph this, you'll see that it'll come right here. It'll never cross the x-axis, but it gets really, really close to it. We'll talk about that more later. It gets really close to it, but it never crosses. This is a growth. This would be a growth domain. Okay, going back, domain. That's x values. So look at your x values. Does it go to the left forever? Yes. It goes up, but is it going to still go to the right forever? Yes. So your domain, all reals. Range, that's y. That's up and down. Does this go down forever? No. Because obviously, that's what I was talking about. No. Right here, it never touches, y equals 0. It never touches the x-axis. It would get really, really close, but it'll never touch it. Does it go up forever? Does it go up? Absolutely it does. So what is your range? Well, remember, using our inequalities, y is greater than 0. When I say y is greater than 0, that means it goes up forever, but it'll never go and never touch y equals 0. Okay, which function best describes the data given? Okay, let's look at these A, B, C, D, E. Look at your options here. Here's your table, and it's really the same table that we just had. So if I was going to graph that, it'd go up just like that. That'd be a growth. And I can see right here, okay, let's look at the ratio. 9 over 3. 27 over 9. 81 over 27. What are those ratios? 9 over 3, that's 3. 27 over 9, that's 3. 81 over 27, that's 3. All the ratios are the same. So again, check the ratio. All the ratios are the same. So I know this is an exponential function. Let's look at our options over here. X squared, that's what we just got done doing. It's quadratic, so it's not A. Okay, well, here's an option. This is an exponential, but this is negative. So looking back at our graph, is this a decay or is this a growth? Well, it's a growth, so it's not B. Again, there's another quadratic, so it's not C. D, 3 raised to the x power, 3 raised to the x power. And you can check it. You can plug in some of these x values in for x, and you'll see that D is the correct answer. All right. Again, this is the start of exponential functions. I'll show you on Monday how to use your calculator to help you out a big time on these. But hopefully we're kind of having a clue now on what's going on, and hope you guys have a really good weekend. Talk to y'all soon.